You have probably taken a dish out of the oven only to be greeted by a gust of hot air blowing from the oven. How can it be that the oven can keep its warmth inside so well? Isolation of heat can be seen everywhere, not only in your oven. Take for instance this picture of a house, taken with an infrared camera. You can see that the windows are much hotter than walls of the house. Hi! In today's lecture we continue looking deeper into heat transport. In the previous lectures we focused on steady-state conduction through simple geometries, such as the flat plate. But heat transport is not only via conduction. Heat can also be transported by convection, that is, by a flow of a liquid or a gas. We use this all the time, for instance in the kitchen when cooking our food in boiling water. We use this when heating our houses in winters and cooling in summers. The picture on the sheet shows an image of a house made by the infrared camera. This reveals large temperature differences on the outside of the house, the walls being much colder than the windows. In the previous lecture we learned how to describe steady-state heat conduction through a flat plate. It is good to memorize this case as it serves as one of the archetypes of heat and mass transfer. We can make an interesting and pretty useful analogy by writing the flux versus driving temperature difference in reversed form. Delta T equals d over lambda times the heat flux. Compare this to Ohm's law describing the current through a resistance when a voltage difference delta V is applied over this resistance. Ohm's law then states delta V equals I times R. Actually, our heat transport problem is quite similar. Delta T plays the role of the voltage difference, while the heat flux is the current. We thus see that d over lambda actually is a resistance, but now to heat flow. Let's use our ideas and the analogy with Ohm's law to consider the case of two flat plates pressed against each other. Again, a temperature difference is present over both plates now. Since there is still a driving force, we expect a resulting heat flux. The question is, what will it be? This system of layers is found frequently. For instance, if you feel cold, you might put on a sweater, thus creating more layers to keep you warm. Answering our question is straightforward if we use Ohm's law. In the picture you saw, you see now two resistors in series. You probably know how to deal with this. We can still write delta V is I times R. But now we need to use the total resistance. For two resistances in series, this is just adding the two. Thus, the total resistance is R1 plus R2. Okay, let's do the heat transfer along the same lines. Also here we have two resistances in series. First, the heat has to flow through the first layer and then through the second. Thus, we write delta T is the flux times the total resistance, which is just like in Ohm's law given by the sum of the two resistances. Each is coming from a steady-state flat plate, and thus of the form d over lambda. We add the two and get d1 over lambda 1 plus d2 over lambda 2. Time for an example, to see how we can use this in practice. Suppose we have an oven in which a heater is present that generates 1 kilowatt of heat inside the oven. The oven is a cube with a wall consisting of 3 layers. These layers have the following properties. The most inner one, the dark blue one, is made of fireproof stone that can withstand the aggressive conditions in the oven. The second, medium blue layer, is a thick layer of isolation material. It is shielded off from the oven conditions by the fireproof layer. Its purpose is to minimize heat losses from the oven to the surroundings. Finally, the light blue layer is wrapped around it to protect the insulation layer. It is made of a thin sheet of steel. The total area of the oven is 1 square meter. Schematically, we can draw the process as follows. On the inside of the oven it is hot. On the outside is room temperature. Aha! A driving force, and thus we expect a heat flow. The question we would like to answer is, what is the steady state temperature inside the oven if the outside is at 20 degrees Celsius? To solve this, we set up a steady state heat balance for the oven. Due to the heat produced, the temperature in the oven will rise. Thus, a driving force will develop, resulting in a heat flow that we also draw in. As always, we start with the general form of the balance. d dt is in minus out plus production, and we will go over all terms. First, the left-hand side. That is 0, as we consider a steady state. No heat flows into the oven, only out, thus the in term is 0. The outflow is unknown yet, and we call it phi sub q. The last term is the production of heat inside the oven. We will call it P, and it has a given value of 1 kilowatt. Thus we can simplify the heat balance to the heat flowing out equals the production. Next, we need to model the heat flow. We now know how to do it. The temperature difference is connected to the heat flow divided by the oven area via the resistance to heat transfer, RQ total. The area is easy. It's given, and it's a meter squared. And, by analogy of Ohm's law, we have that the resistance is the sum of 3 resistances of the layers. Let's repeat the major steps. We found that the heat flux equals the heat production. We modeled the heat flux in terms of the total heat resistance R sub Q tot. From these two equations we solve the temperature difference. Next, we use that the total resistance is equal to the sum of heat resistances. If we put in numbers, we find for the heat resistance 0.23 watt per Kelvin and compute for delta T 234 Kelvin. Thus, the inside of the oven has a steady state temperature of 527 degrees Celsius. The concept of a driving temperature difference giving rise to a heat flow is also applicable to more complex situations. For instance, when convection of heat is present in a heat exchanger, or during cooling down of a hot object when the heat transfer problem is transient. Therefore, we couple the driving temperature difference to a resulting heat flow in what is called Newton's cooling law. That reads as phi sub q equals h times a times delta T. This law directly reflects that a temperature difference leads to a heat flow. It further takes into account that we expect the flow to be proportional to the area available for heat transport. Obviously, all kinds of details concerning the geometry, the materials involved, and whether or not there is convective transport are not captured by A times delta T. Therefore, a coefficient h is put in front of A times delta T. This is the so-called heat transfer coefficient. For different situations, h will take on different forms. For now, it's sufficient to think of h as a given quantity that describes how effective the heat transport is. Rather than writing phi q as a function of delta T, we can also invert this equation and write delta T as a function of the heat transport. Obviously, we now find on the right-hand side 1 over h as the coupling constant. As we have seen, this is very much like Ohm's law. A voltage difference across a resistor leads to a current. According to Ohm, the current and the voltage difference are related via delta V is I times R with RD resistance. If we look at our equation on the top right of the sheet, it looks the same. Thus we see that 1 over h can be interpreted as resistance. Now of course resistance to heat. This turns out to be a very handy concept. Temperature differences give rise to heat flows. How large the heat flow is depends on the heat resistance. The higher the resistance, the smaller the heat flow. Note that for the heat transfer coefficient H, the reverse holds. The larger H, the larger the heat flow. That is no surprise. After all, H is a transfer coefficient, not a resistance. With the concept of Newton's cooling law and the heat transfer coefficient H, we can summarize the results of steady-state conduction in a simple way. For instance, the case of the flat plate is completely characterized by saying that H is equal to lambda over d. Similarly, steady-state heat conduction through a cylindrical wall is given by H is lambda over the outer radius and over the natural logarithm of the ratio of outer to inner diameter. Likewise, steady-state conduction from a surface of a sphere into the surrounding medium is captured by stating H equals lambda over the radius of the sphere. These compact forms are very useful when it comes to problem solving. We will see this in the examples and exercises. It is common practice to try and formulate quantities like H not in a dimensional form like in the previous sheet, but in a non-dimensional form. This makes that we can use the resulting non-dimensional relations on a wide range of applications. We already saw an example in the lectures on the drag force where we used the Reynolds number rather than the velocity when we had to deal with the drag coefficient. CD turned out to be a function of Reynolds, and it didn't matter whether we were dealing with an object falling through air or through water. The same CD curve applied. We introduce the Nusselt number as the non-dimensional form of H. It is by definition the ratio of the resistance of steady-state conduction through a flat plate over the true resistance in the problem at hand. Thus, Reynolds is d over lambda divided by 1 over h, or in simplified form, Nusselt is dh over lambda. This can be written in another way. H is Nusselt times lambda over d. This form shows that to a first approximation the heat transfer coefficient is given by our archetype, the flat plate. Everything that is different from the case we are actually considering is put in the Nusselt number. We can write our results for the steady-state cases now even more compact. For a flat plate, it is obvious that Nusselt is 1. For the sphere, we first write the heat transfer coefficient in terms of the diameter rather than the radius. Thus, h is 2 lambda over d. This means that we get Nusselt is 2. The case of the cylinder is also given in the table. What happens when heat is flowing through an interface that separates two different media? In general, different ways of heat transfer are possible. We have seen one example when we studied conduction through two flat layers. The picture on the sheet shows the two sides of an interface. The light blue part, where away from the interface the temperature is high, and the dark blue part, that away from the interface has a lower temperature. Clearly a driving different temperature is present, and we may expect a resulting heat flow. Note that we draw this heat flow in the light blue as well as in the dark blue part. We can write this according to Newton's cooling law as phi sub q is U A times delta T. Here U denotes the total heat transfer coefficient, and the question is, what is U in terms of the heat transfer coefficient on each side of the interface? To find the answer, we are going to describe the heat flow on each side of the interface. First, we introduce the temperature T sub I of the interface. Next, we write for the light blue part the heat flux caused by the driving temperature difference for the light blue part. Phi double dash sub q is equal to H1 times T1 minus T interface. We do the same for the heat flux on the dark blue side and find that phi double dash sub q equals H2 times T interface minus T2. It is important to see that we did not give the two heat fluxes each a separated index 1 or 2. Why not? Well, the heat flux in the light blue part is from the bulk of the light blue to the interface. Once the heat arrives at the interface, it has only two options. Either it's stored in the interface or it continues in the dark blue part. But an interface has zero thickness. It has no volume. Thus it cannot store any heat, and we have to conclude that all heat entering the interface from the light blue side has to leave the interface from the dark blue side. In other words, both heat fluxes are the same. We can invert both fluxes to single out the unknown interface temperature. This step is also shown on the sheet. By adding these two equations, we see that the interface temperature Ti drops out of the equation, and we get the temperature difference is indeed proportional to the heat flux. This is Newton's cooling law in reversed form. If we compare this with the general form given above, we find for the total heat coefficient U that 1 over U equals 1 over H1 plus 1 over H2. No surprises, isn't it? This just states that the total resistance is the sum of the two resistances who are in series, just as we could have expected from Ohm's law. In this sheet, we summarize what we find. What is new to this analysis compared to the case of two flat plates pushed against each other? Nothing really. Only in the case on the present sheet, we did not have to use that it is about flat plates with conduction. Again, we found that the total resistance is the sum of the two resistances on either side of the interface. The result we have derived here is much more general. It holds for all kinds of heat transfer problems, with heat going through an interface, no matter what geometry and no matter whether it's a conduction, convection or a mixed form of heat transfer. With this, our lecture is ending. Behind me, we can see the infrared photo of the house again. In one of the example videos, we will calculate the heat loss through a single glassed window. You can also put what you have learned today into practice by going to the exercises and calculating how much money you can save by switching from single to double glazed windows. While making the exercises, it is useful to start thinking in terms of driving forces resulting in flows and, most importantly, resistances. Good luck until next lecture.